Welcome back to RamZland. I'm so glad that you could join us for this lesson today. The objective in this lesson is to review Euler's formula as it pertains to polyhedron. So let's start out and talk about what does the word polyhedron mean? In Latin, the word poly means many. The word hedron means faces. So when we talk about a platonic solid, we're talking about a three-dimensional object that has many faces. Now, when you think about polyhedron, most questions pertain to how many edges, how many faces, or how many vertices the polyhedron have. So I want to give you some examples of what these look like and how to use Euler's formula to determine faces, edges, and vertices. And if you look in this first example, I just want to use these shapes to help you identify the difference between like a face and an edge. So first of all, a face is a flat surface on a three-dimensional figure that's convex. So when I look at a cube, or we're going to call it a hexahedron, because a cube has 6 faces. So a hexahedron has several edges. And where 2 faces meet, it creates an edge. Where 2 edges meet, it creates a vertice, or what you would think of as a corner. So these corners here, these are called vertices. And these flat surfaces are called faces. And where 2 faces meet are called edges. This is an edge right here. Now, for a lot of these shapes, you can just look at them and simply count the number of vertices and the number of edges. But as these shapes get larger, using Euler's formula makes it much easier. So if I look at a hexahedron, or a cube, if you will, I can see very easily that it has 6 faces. It has 4 going around, and of course it has a top and a bottom. So I would say a hexahedron has 6 faces. Now if I wanted to see how many vertices it would have, you could either count all these or you could use Euler's formula, and you'd see that a hexahedron or a cube has a total of 8 vertices. And then the edges are where 2 faces meet. So on the bottom, you'd of course have 4 edges. You go around it, you have 4 more, and then 4 more edges on the top for a total of 12 edges. So this is Euler's formula, and you can write this formula different ways. One way you can write it is faces plus vertices minus 2 equals edges. That's one way you can write it. Let's try that out. So if my face is 6, I'd have 6 plus my vertices is 8 minus 2. Does that equal my edges? My edges is 12. 6 plus 8, that's 14. Minus 2 equals 12. This is called Euler's formula. Let's see what it looks like for this triangular prism. So my faces, I'd have a top and a bottom, so that's 2. Of course, I have the bottom and the 3 going around it, so I have a total of 5 faces. Let's look at the vertices. I have 1, 2, 3, 4, 5, 6 vertices. And I could count the edges. Of course, I have 3 on the bottom, 3 more going around it. I have 3 edges on the top. That's 9. Let's say that I didn't have a picture, so I can count it. Let's see if I can use Euler's formula right here. Again, I have faces plus vertices minus 2 equals edges. So my face is 5. 5 plus 6 minus 2. Does that equal 9? 5 plus 6 is 11 minus 2 equals 9. And so here again, we can see using Euler's formula, it makes it a little bit simpler. Now let's look at a sphere. So for a sphere, it does have one face. That's the lateral edge of the object. So we could say there's one face. But a sphere has 0 vertices. It has 0 edges. Okay? Let's look at a few more where I can use Euler's formula. I can use Euler's formula for a square pyramid. So I have 1, 2, 3, 4, 5 vertices. Okay? Now the bottom of it counts as a face. So I have 4 faces going around it plus the bottom is 5. Well, faces equals 5. Now if I wanted to look at edges, I have 4 edges on the bottom down here. And then I have 4 edges going around it. You can barely see that one there. So for edges, I have 8. So let's look at our formula again. So faces plus vertices minus 2 equals edges. So faces and vertices would be 5 plus 5, that's our vertice, minus our edges. So I have 5 plus 5 is 10 minus 2, and our edge was 8, right? And I know 10 minus 2 equals 8. So my formula works. Let's try it for a triangular prism now. So let's do vertices. So I have 1, 2, 3, 4, 5, like 6 vertices. Let's try edges. I have 1, 2, 3 on the bottom, 4, 5, 6, 7, 8, 9 edges. Let's look at our faces. So I have the bottom of it, and I have the 2 ends. That's 3, 4, 5. Let's count that again. 1, 2, and the bottom is 3, 4, 5. So 5 faces. Okay, here's the formula I want you to use. So faces plus vertices would be 5 plus 6. This is minus 2. Minus 2 equals edges. 5 plus 6 is 11. 11 minus 2. Does that equal 9? Our edge is 9. It looks like it does. 9 equals 9. Okay? All right, let's name some solid figures before we take another look at Euler's formula here. Again, when you see cube or rectangular prism, I want you to use this term, hexahedron. Okay? When you see triangular pyramid, I don't want you to use that. I want you to use the phrase tetrahedron. Okay? That's more in the classical sense there. Hexahedron, tetrahedron. And for the prism, triangular prism, that's fine. Sphere, cone, cylinder, it's fine. Let's look at how this pertains to like a formal look at Euler's formula with our pictures here. So here's another way that you can write the formula right here. What I would like to see is your understanding this can be written in many different ways. So you could write this faces plus vertices minus 2 equals edges. That's just flipping around this equation. You could write vertices minus, that's how they have vertices minus edges plus faces equals 2. And these are the natural that Plato used. And so there are 5 natural ones. When the polygons, which are the faces, are all equivalent. They're all the same size, okay? So for the tetrahedron, some people call this a triangular pyramid. Don't call it that. Call it a tetrahedron. You can see these are all equilateral triangles that are joined together. So for a tetrahedron, you're going to have 4 faces. You're going to have 1, 2, 3, 4. You're going to have 4 vertices. And then edges, you're going to have the 3 edges on the bottom, and you're going to have the 3 edges on the top. So for edges, you should have 6, okay? For a cube, you can see your, what we're going to call hexahedron. For the cube, you've got your 4 vertices on the top and your 4 vertices on the bottom. So vertices is 8, faces is 6, edges should be 12. The octahedron, this is a classical polyhedron because again, all of your triangles are equal. So each triangle is the same size. And you can see an octahedron, octa, like an octopus, octa means 8. So you're going to have 8 faces. Let's look at vertices. You have 1, 2, 3, 4, 5, and then the bottom would be 6. So vertices is going to be 6. Let's look at your edges. You have 4 edges on the bottom, 4 edges in the middle, and 4 edges on top, so 12. Okay? So if I use my formula right here, if I did this, if I did faces plus vertices, that would be 8 plus 6 minus 2 equals 12. So 8 plus 6 is 14. 14 minus 2 equals 12. Okay? Now, if I use this way, if I use the formula and I rewrote it this way, this is what it would look like. I would have vertices minus edges. So 8 minus 6 plus 12 equals 2. And you can see here, if I had 6 minus 8, and how that works out. If we go down a little bit further down, you can see more examples. Here they're calling it a tetrahedron instead of a triangular pyramid, like that. That's the octahedron. I want to look at some larger examples with you, the dodecahedron, which I think is in this example right here. Here's the formula again, for Euler's formula. Let's look at some large, okay, so here, regular polygons must be convex. You can't have any concave faces. Okay, here are the 5 shapes, okay? So here's your tetrahedron. Here's your hexahedron. This is your octahedron. This right here has 12 faces. Is called a dodecahedron. And the one that has 20 faces, equilateral triangles, that's called an icosahedron. And I want to look at how to find this. So here's your edges, faces, vertices that they're filling out in a graph here. With that Euclidean formula right here. And that's just showing you there's proof that there's 5 platonic solids for the formula. Okay, and so here you can see the edges very clearly for the hexahedron. And you can see for edges you have 12, for faces you have 6, and of course for vertices you have 8. So if I use my formula, faces plus vertices minus 2 equals edges, you can solve for that. So what I'd like to do is, if you have some paper, I would like to try to use this formula, Euler's formula, for a series of pyramids and prisms that I'd like you to practice drawing and actually use the formula for each drawing. So I'm going to pull up on my computer just a blank screen, and I'm just going to use paint for this. But the first thing I'd like to do is just draw your tetrahedron. And this is with a triangle. And pick a vertice or an apex where all the vertices meet, because these are pyramids. And try to draw that with me. Okay. So this is the tetrahedron. And for a tetrahedron, we're going to have, going to make faces, edges, and vertices. Okay. Okay, so I know I have 1, 2, 3, 4 vertices. And for edges, I have 1, 2, 3, 4, 5, 6 edges. And for faces, I have 3 going around and the bottom, which would be 4. Okay? So if I use my formula, faces plus vertices minus 2 equals edges, let's see if that works. So I have 4 plus 4 minus 2 has to equal my edges, which was 6. And I know 4 plus 4 is 8 minus 2 equals 6. okay? Let's try another one. So this is your square pyramid. So I'm going to draw a square. We're going to test it for Euler's formula. I'm going to pick an apex anywhere, maybe over here. Connect all my vertices to that apex. Okay? This is my square pyramid. So again, let's try this for faces, edges, and vertices. So for faces, I have the base of it, and then I have 4 faces going around my pyramid. So that's 5 faces. For edges, I have 1, 2, 3, 4 edges on the bottom, and of course, 4 edges going around the pyramid. So I have 8 edges. For vertices, I'm going to have 1, 2, 3, 4 plus the apex. That counts as the vertice. So I have 5 vertices. Okay? So let's see how this works in Euler's formula. So I have faces plus vertices. That's 5 plus 5. 5 plus 5 minus 2 equals my edges, which is 8. So I know 5 plus 5 is 10 minus 2. And that equals 8. Okay, so that was the square pyramid. Let's try a pentagonal pyramid. So I'm going to draw a pentagon. I'm going to pick an apex over here somewhere. I'm going to connect all my vertices to that apex. Try drawing this with me as we go along. I think it helps when you draw these. Okay. So I'm going to look at my faces, edges, vertices here. Let me look at my drawing. That faces, this is faces, edges, vertices. And let's plug in our data together. Okay, so my face, I have a face on the bottom, plus I have 5 going around it. So face. And for my edges, I have 5 on the bottom, and I have 5 edges going around it. So I have 10 edges. And for my vertices, I have the apex plus the 5 vertices on the bottom, which makes 6 vertices for my pentagonal pyramid. Okay, let's see if this works with Euler's formula. Okay, so this is Euler's theorem or formula. And Euler's formula says faces plus vertices minus 2 equals edges. Let's try that. 6 plus 6 minus 2, does that equal 10? Let's find out. 6 plus 6 is 12, minus 2 equals 10. So for the square pyramid, the pentagonal pyramid, it works, okay? Let's try one more. Let's try a prism this time. Remember, prism has a congruent top and bottom that matches, okay? So here's my faces, edges, and vertices. And for this prism, let's make a triangular prism. So I'm going to draw an equilateral triangle here and an equilateral triangle here. I'm going to connect all my vertices, the top to the top, the bottom left to the bottom left, the bottom right to the bottom right. And I'm going to look at first at my faces. So I have the 3 faces going around it plus the end. So I have 5 faces. For edges, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 9 edges. For vertices, I have 3 at one end, and I have 3 vertices at the other end. So it looks like I have a total of 6 vertices. Let's use Euler's formula. I have faces plus vertices. So I have 5 plus 6. 5 plus 6 minus 2 is supposed to equal my edges, which was 9. So I know 5 plus 6 is 11. Minus 2 equals 9. So it works. So hopefully in this lesson, you're getting an idea of the difference between an edge, a vertice, and a face. You're seeing how you can use Euler's formula to figure out how many faces, edges, or vertices these have. Because some of these are really complex. If you take a look at pictures of the icosahedron, which I think I had over here, it becomes kind of difficult to see how many edges and vertices a really large shape has. Of course, you just remember icosa is, 20 faces, but if you can't see all of them, it's a little bit difficult. Let me see if I have pictures of that here. Icosahedron. Here we go. So here's your icosahedron. So I know icosa has 20 faces, but for edges, it's kind of difficult. Icosahedron has 30 edges, and it has 12 vertices. For vertices, that's for the icosahedron. Or I could use Euler's formula, which would make that a lot easier to figure out. Dodeca means 12, so I have 12 faces. Again, you have 30 edges for the dodecahedron. And then you have 20 vertices for this one. So let's go back and review some of the things we've talked about. So hopefully in this lesson, you've learned the difference between a face, an edge, and a vertice. Remember, a face is where two edges come together. A vertice is like a corner of a three-dimensional shape. Hopefully in this lesson, you've learned Euler's formula, which can be written as faces plus edges minus 2, faces plus vertices minus 2 equals edges. You can always use Euler's formula also as vertices minus edges plus faces equals 2. You could do it that way. There's different ways that you can organize the equation. Hopefully you learned in this that a platonic solid, a natural platonic solid, there's only 5 of them. So you have your hexahedron, that's a cube. You have a tetrahedron, that's like a triangular pyramid. You have an octahedron, that's the one with 8 faces. The dodecahedron, that's the one that looks like a soccer ball, it has 12 faces. And the icosahedron, that's the one that has 20 faces. Hopefully you learned that all the faces have to be congruent for it to be a natural polyhedron. They all have to be the same size shapes. So if they're triangles, they all have to be equilateral triangles of the same size. If they're pentagons, they all have to be equilateral pentagons of the same shape. Of course, if it's a square for a hexahedron, all the squares have to be equal. You can't have like one big square attached to another square. Another thing that I want to review in this lesson is when you'll have a question and I'll say, use Euler's formula to figure out how many edges, vertices, and faces a geometric net has. And a geometric net is when you still have a platonic solid, it's still a polyhedron, but it looks like it's unfolded. So instead of being three-dimensional, it's flat. And I want to show you some examples of what those look like really quickly. And I'm going to go back to our open screen here and hopefully just open a new one and zoom in on this so that you can see it easily. And when we look at a geometric net for a hexahedron, you should see 6 squares that are all equal, but each square is unfolded, so it should look flat. This is one way that you can draw a geometric net for a hexahedron. So again, if you folded all this, it would look like a cube. So this square would be the bottom. This square right here, if you folded it upward, this square would be the top. These would be the sides of the box if it's unfolded. This is a side. This over here would be a side. And this would be a side. Now, when you look at a geometric net, these are called nets. One thing that's really easy to see in a geometric net is the number of faces that the polyhedron has. So I can very quickly count, okay, that's 1, 2, 3, 4, 5. I can see this is 6 faces. So really quickly I can say, okay, this is obviously a hexahedron because it has 6 faces. One thing that's not easy to count on this are the vertices. So when it's unfolded and flat like this, it's not very easy to see the number of vertices because when it folds together, those faces share vertices. So that's where you'd want to actually draw it as a three-dimensional object instead of being flat. Because now I can count 1, 2, 3, 4, 5, 6, 7, 8. I can clearly see 8 vertices at that point. Now you'll have other geometric nets that are unfolded. So if I went back to my tetrahedron, and I wanted to see what a geometric net looked like for a tetrahedron, I would draw an equilateral triangle, but then on each side, there's another equilateral triangle. So this is a net for a tetrahedron. Again, the advantage for geometric nets is for seeing faces. I can very clearly see there's 1, 2, 3, 4 faces. Okay? I can't, however, really see the edges or the vertices clearly, so I might draw it three-dimensionally like this. Pick an apex and connect all of your vertices to it. So I have 1, 2, 3, 4. So I have 4 vertices. And I might be able to see the edges more clearly now too, because those triangles share edges when they're three-dimensional. So I have 1, 2, 3 edges on the bottom, 4, 5, 6. So now I have 6 edges. But up here, that might be more difficult to see the 6 edges when it's a geometric net, okay? So when you're using Euler's formula, remember, sometimes you'll have a question and the picture that you're looking at, it's not three-dimensional. It's flat like that. That's called the geometric net. Knowing how to draw them three-dimensionally and practicing that will help you a lot. When it is three-dimensional, you can see that where 2 edges meet, that creates a vertice, okay? And where 2 faces meet, that creates an edge. And you can count those and see those pretty clearly. And if you only have some of the information, then you can use Euler's formula to figure out how many vertices or how many edges the platonic solid has. Wanted to talk to you in this lesson a little bit about who Euler is. So Leonardo Euler lived in the 1700s, and I have a picture of him, and I wanted to share that with you really quick in this lesson here. So if we go up to the top of this, we should have a picture of him right here. Here he is. This is Leonardo Euler, and he lived in the 1700s mostly, and he was a Swiss mathematician who realized that there was a relationship between edges, faces, and vertices. And so we are using this man's research hundreds of years later today in mathematics, and that just kind of gives you a background of who he is and why he's important. I wanted to talk about some irregular shapes before we end this lesson that still have faces, edges, but may not have vertices. So if someone asks you how many vertices a cylinder has, it has 0. There are 0 corners on a cylinder. For edges, you would count this top edge here and this bottom edge, even though it's a lateral edge, it's curved, it still counts. So you'd say it has 2 edges. For faces, you have the top and the bottom, and you have the lateral surface on a cylinder. So for faces, you'd actually have 3. Now let's take a look at a cone. This is not a natural platonic solid because it doesn't have equilateral polygons that are attached. You've got, for faces, you have this lateral face that's curved, and then you have the bottom. So you only have 2 faces on a cone. For edges, this point up here, this lateral edge right here, this would have 1 edge. This is a vertice up here. So this edge over here is a lateral surface, so you'd have 1 edge. For vertices, you just have the top vertice, just 1. A sphere is kind of a trick question. A sphere has 1 face, it's a lateral face, it's curved, but you don't have any edges. So edges would be 0, vertices would be 0. For a sphere. If I look over here, I've got some shapes that I want to talk about here. If you have a front and a back that are the same equilateral polygons, and the front and the back are attached by squares or rectangles, that's always a prism, okay? So I know this is a prism because the top and the bottom are the same, it's connected by rectangles. So whatever the top and the bottom is, that's the name of the prism. So this one has a triangle in the top and the bottom. So this is called a triangular prism. This one does not have a triangle. It has a rectangle on the top and the bottom. So you just call this a rectangular prism. And then over here, this is not a prism because the bottom is a square, but the top is not a square. It has what's called an apex. So if you have a place on a platonic solid where all the vertices connect, so all 4 of these vertices connect at this one point right here called an apex, that's a type of pyramid. You name the pyramid by the base. So the base of this is a square, so I would call this a square pyramid. Like the pyramids of Giza in Egypt. Those are square pyramids. They're not tetrahedron, okay? Okay, so let's go back and review a little bit more. So we talked about geometric nets. We talked about Euler's formula and how we find the edges, faces, and vertices on a platonic solid. We reviewed that all platonic solids, really the natural ones, there's only 5 of them. And we reviewed that the polygons have to be congruent polygons that are connected to each other to make one of the 5 normal polyhedron. We reviewed that icosa has 20 faces, a dodecahedron has 12 faces. So I'm hoping that this information will help you with some geometry questions that you might have. And if you need to go back and rewatch this video, we're gonna post it on our math YouTube channel. I hope some of you have been able to find that and been able to subscribe and review some of those questions because you guys are the stars of the channel. It's all you, okay? Our next class is gonna be on Wednesday, same time, and I hope to see you then. Thank you for coming and have a great evening, okay?
Thank you. You too, teacher.
Okay, bye-bye.
Bye.